Yeah, thank you for reminding me. Yeah, so another small point I wanted to say, as I said, I'll discuss all administrative things later. But let me just mention that this course, because many of you have written to me, and I think there are people from a diverse set of backgrounds. We will get to know more of you later. But the thing is this, so this is a compulsory course for integrated PhD. They have no choice. Okay, so in PhD first year, second semester students, well, you are doomed, so you don't have any choice. Okay, what about the undergraduates? Undergraduates can take this in 6th semester or 8th semester. And I believe there are some second year students also who wanted to take, and I have no objection. But having said that, let me say that the general experience appears to be that this is one of the difficult courses. I cannot say why. Uh, it requires a little mathematical maturity for sure, compared to the first semester courses, real analysis and so on. And compared to other courses at the same time that you could take, like complex analysis, the advantage in complex analysis is it's too clean a subject. Now, measure theory is not clean. It is like analysis. So you have to get your hands dirty. You will see that there are details, many things. So complex analysis is a bit unusually clean subject. Okay, so in that sense, maybe that is what makes it difficult. I don't know. Anyway, the option is there to take it in 6th semester or the 8th semester, and I have absolutely no objection to anybody wanting to take it. But please be realistic, watch yourself, and if it gets too difficult, drop it. You can take help from me, from the TA and so on, so to know what it is going to be like after a little while. But hopefully in the first few weeks you get an idea of the nature of the subject. Okay, and if it gets difficult, don't hesitate to drop. Okay, so but after that, if you stay on, it is your responsibility. I'm happy to help with the subject, but yeah, exams, everything, you have to deal with it, and solving problems is absolutely important. And we will be having many problem sets and some midterms and final, about which we will discuss later. Okay, so that is about the course. And reference books I have put there. Okay, so that I talked about last time. Okay, now let's go to the actual subject. Okay, so now let's start the actual subject. So what we want to talk about is this business of lengths, areas, volume. So let's start with the real line, simplest, and talk about lengths of subsets. Okay, so we want to, for a subset of real line, can we associate a length to it, and how far can we go with it? Okay, so first of all, if I is an interval, if, if I is an interval could be open interval, closed interval, or it could be one-sided closed, or well, other sided closed, one side open, other side closed, whatever it is. Then its length is, we know what we want its length to be, b minus a. For all of this, we would like the length to be b minus a. That much is clear to start with. Okay, so we will denote it as, only for interval I will do this, or will more generally, when we talk about the length of a set, we will use the symbol lambda of I for the length of a set. But just for intervals, I will also use this absolute value like notation. So just for intervals, okay. Okay, so that much is clear. So what else is clear? So can we associate length to anything? Okay, if a set A is a union of intervals, let's say it's a disjoint union of intervals, finitely many. So by this square union means that it is just means it is a pairwise disjoint union.
Sir, have you shared your screen? I think I can't see.
Oh, is that so?
Yeah.
Uh,
No, we can see it.
I can see
Yeah,
it.
we can see it, sir.
you can see it. Okay, so who is having the problem?
Yes, sir.
So can I know who is having the problem?
Anirban. Okay, I'll check my probably connection issues. I'll check.
Yeah, maybe just logging out and coming back will help. But if in a minute you don't see it, please interrupt me again because you should be. Is there anyone else who is unable to see? So this is unable, right? So can you see it now by any chance? Unable?
So, your voice broke. Can you repeat the question?
Can you see? Can you see? No, I was asking Anirban who was not able to see the screen. Can you see it now?
I
Okay.
think I have some internet issues. I'll try to refresh.
Okay. Yeah, but if it persists, please let me know. Yeah, if everyone else is able to see, then maybe the problem is on that side. Okay. Yeah, but maybe I'll give you a minute to join. I mean, you want to try? Is there a question here? So there is a hand raised.
Yeah, quick question. Can I ask what is the significance of pairwise disjoint? You can just say disjoint.
Oh, pairwise means I mean everyone is disjoint from every other. So well, that's what usually mean when people say disjoint, but so disjoint doesn't mean the overall intersection is empty. I mean every pair the intersection is empty. I1 has no intersection with I2, I1 has no intersection with I3 and so on.
Okay, thank you.
Okay. Yeah, so well, see the thing is, I mean maybe I don't know, maybe people don't say pairwise disjoint, but I am a probabilist and there we talk about independence where it goes the other way. So we are very careful to say independent versus pairwise independent. So that's, I mean, so I'm just extra careful in the language. That's all. Okay, so maybe I continue now. Okay, so if anyone comes back and has difficulties, we'll see. So suppose, so for intervals, we are clear. Yes?
Now it is visible. I refreshed. Okay.
Okay, very good, very good. Okay. Okay, so what I have said so far is that for intervals, we know what the length should be. And another class of sets for which we are particular what the length should be is if suppose we have this A is a subset which is a finite union of pairwise disjoint intervals. Okay, pairwise disjoint and each ij is an interval. Then we know that the length of that should be just the sum of lengths. Okay, this much we know we want. I mean, so this is we want this. This much is clear, and then what else can we work with? So this type of set we'll call it. Let's just it's not some standard name. Let's call it elementary set. It's a local. I mean local. I mean for now I will just when I say elementary set, I mean a finite union of intervals. They are pairwise disjoint. It doesn't matter they're open, closed, whatever. I don't care. So it was all the same. Okay. So now, what else can we do? So for that, before saying what else can we define length for, we should know what do we want out of length. Okay. So what are we asking for out of length? There has to be some requirement. Okay. Let's start with the least controversial one. There can be no controversy about this. So what do we want length to satisfy? Okay. So I won't say all the things straight out. So one thing, no controversy, is that monotonicity should be true. Okay. That is, if A is contained in B, then length of A should not be more than length of B. That much is I think nobody disputes this, right? Nobody disputes that we should have monotonicity, that a smaller set, that is, if A is contained in B, then length of A should not be more than length of B. Okay, that much is clear. So, but that already suggests something. Okay, if I have some set, so what that suggests is the following. Suppose I take, if A is contained in R, an arbitrary set, subset. Suppose I take any arbitrary subset of the real line. Now, what should its length be? I just, based on monotonicity, I know that if, suppose, okay, let me say first in words. I know I have this class of sets for which I have already defined length, namely elementary sets, which includes intervals also. So if A is contained in some elementary set, it should, whatever length we assign to A should not be more than the length of that elementary set. We agree, right? By monotonicity, if A is contained in some elementary set, its length, the length of A should not be more than the length of that elementary set. Similarly, if some elementary set is contained inside A, then the length of A should be at least as large as the length of that elementary set. So this is just from monotonicity that we are going to require. So what this suggests is, let us consider, you take the length of any elementary set. So you take any I1. So let me just write like this. Instead of writing elementary set, I write like this. This is a pairwise disjoint union of intervals. If it contains A, then I calculate its length, which is the sum of the lengths of the intervals, j equals 1 to k. So for any such thing, this should be more than the length of A. So if I take the infimum also, I take infimum over all k greater than or equal to 0 and ij are intervals such that, and this square union means that they are pairwise disjoint. Actually, okay, in this case, it doesn't matter if they are pairwise disjoint or not, but let's say, yeah, actually it doesn't matter whether they are, even if they are not disjoint, then this should only be worse, right? Okay, but if you want, let's write pairwise disjoint. Yeah, so should I keep it or should I not keep it? It's okay, I can keep it. So then the infimum should be, so let's call it, oops. So let's give it a name. Let's call it lambda super hash of A. Okay. Similarly, I define lambda lower hash of A is infimum of the sum of lengths. So that is infimum of the, sorry, not infimum, supremum of the lengths of elementary sets contained inside. I take supremum of length of any elementary set such that I1 okay is contained inside of it. Okay, so this is what we do. Yeah, so then right, so then so this is, suppose this is how we define it. So this is like way, I mean, you see where the idea is from. This is the idea like upper and lower sums in integration. So what we do there is, in upper and lower sums in integration in Riemann integral, what we were doing was something like the same. So there was a graph of a function, and we have this irregular region for which we had to measure the area. And then it was enclosed inside and outside by some simple regions, namely unions of rectangles. So something like, if we take these rectangles, so we enclose it by rectangles, and anyway you enclose it by rectangles, the length of the sum of the areas of the rectangle should beat the area of the figure that you are trying to define. I mean, whose area you are trying to define. Similarly, if you have some bunch of things, bunch of rectangles which are contained inside, it could be like this. So you have these rectangles, so union of rectangles which are contained inside the region. Then the area that you are going to assign to your region should be more than the sum of the areas of those red rectangles. Okay, so the same idea we are sort of using here based on something we already know. If A is contained in an elementary set, your length should be not more than that. So so in other words, what we are very clear about is the length of A should not be more than lambda super hash of A, and length of A should not be less than lambda lower hash of A. Right, that much is clear. So whatever be, just monotonicity tells you that length should be between these two numbers. So you see that lambda lower hash is smaller than or equal to lambda upper hash. That is clear, right? Because again, by monotonicity, this is a supremum over a set of numbers, this is infimum over a set of numbers, and you can see that any set of numbers here is smaller than any set of numbers in the upper set. Because you take I1, I2, Ik, which is contained, whose union is contained in A, and J1, J2, JL, whose union contains A, then I1, I2, Ik is contained in J1 union, J2 union, JL. Therefore, every number in the second set is smaller than every number in the first set. Therefore, this is less than equal to, so that is clear. So, whatever be length, so in other words, by monotonicity, requirement, we want length of A to be at most lambda super hash of A and at least lambda lower hash of A. This much is clear. So at least if we are lucky and these two happen to be the same, then we have no doubt what the length should be. That is the definition of Jordan measurable set. Okay. So definition. If
Sir,
yes.
so sir, why do we need A to be contained in an elementary set? I mean, in general, isn't it true that any A will be always contained in elementary set?
Say it again here. The first definition you're saying.
Yeah, you just mentioned.
No, I take any possible way of containing A inside an elementary set. Okay, see, the elementary sets are the only sets for which I know the length at the moment. And I am going to try to define length for other sets.
Okay.
So since I know the lengths of elementary sets, what I know for sure is whatever my set is, if it's contained inside some elementary set, its length should be smaller than the length of that elementary set. And if it contains an elementary set, its length should be at least as large as the length of that elementary set. These are the only points I know at the moment based on monotonicity.
Okay.
Therefore, any such thing, so for any such covering of A by these disjoint intervals, this should beat length. So I take the infimum, that should also beat the length. And same for the other side. Is it clear?
Yes, yes.
Okay.
Yes.
Okay. So that's how we want it to be. So if we are lucky and it happens that lambda lower hash of A equal to lambda upper hash of A, we say that A is Jordan measurable and define its length lambda of A to be the same, the common value, which is equal to lambda lower hash. Okay. So that is in the cases when you are lucky, you say that, okay, you know what the length should be. Since I made a definition, it is pretty clear that if it was the case that for all sets, these two would match, I would have stated a theorem. So it's kind of clear it's not. So we will see example in a moment. So this is not controversial. So this is how it has to be. So let's see an example of a Jordan measurable set and something that's also not Jordan measurable. So suppose I take A is a finite set. So suppose A is some finite set, x1, x2, xn. So then A can be contained in, I can do x1 minus epsilon, x1 plus epsilon, union, xn minus epsilon, xn plus epsilon. Okay, this is a disjoint union if epsilon is small enough. If you take a large epsilon, of course, these intervals might well intersect. But if you take a small enough epsilon, there is some finite distance between any pair of xi's, right? Say x1 and x2, x3, whatever be the nearest distance between two distinct xi's. If you take epsilon to be smaller than half of that, then these things will be disjoint, and A is contained in this. So which implies that since this is an elementary set, its sum of lengths should be less than, that is 2 epsilon n, should beat lambda hash of A, because lambda hash of A is the infimum of all such things. So it should be smaller than that. As epsilon is arbitrary, n is fixed, A is a fixed set, epsilon is arbitrary. We see that lambda super hash of A is 0. Now I don't need to check lambda lower hash of A. It's always greater than equal to 0, because this is never, there is always the empty set for which we assign the length 0. Okay, that is what is meant here. Here empty set is also there. Yeah, one thing one should be slightly careful in definitions is infimum of an empty set is we always define to be. So convention is that infimum of empty set will be minus infinity and supremum of empty set is plus infinity. That is the usual convention, which is the most convenient way. Unless I say otherwise, that will be the convention. But here it is never, these two collections are never empty, because I include empty set here. I mean, so the upper one is okay. I mean, so right. I allow infinite intervals also, by the way. I allow infinite intervals also, which have infinite length. And I also allow empty set as an interval. So there is always that empty set. So these suprema and infimum
It's 4 o'clock.
Are over non-empty collections. Anyway, so therefore this lambda super hash of A is 0. And anyway, so lambda lower hash is at least 0. Always. So in general, this can be infinity also. That's the point. So this is always get to the, in general, this is true. That can be infinity, but so here it is true. So A is Jordan measurable. And lambda of A is 0. This is clear. Okay. So now let's give an example. Another example of something which is not Jordan measurable. Okay, so can you give me an example of a set which will not be Jordan measurable? Anyone?
Cantor set.
Cantor set, okay, it's a good candidate. So whenever you are looking for counterexamples, Cantor set is a good one. So since you mentioned it, let's take the 1/3 Cantor set. Okay, so let's just quickly recall Cantor set. You start with the full interval, that is K0, is the interval 0 to 1, and then you take this, you delete the middle 1/3, and K1 is 0, 1/3 to 2/3 1, and so on. Next K2, I'll not write a picture, it will be a union of 4 intervals, 0, 1/9, 2/9 to 1/3, union, what is that? 2/3 is 6/9, to 7/9 union 8/9 to 1. So it's a union of 4 intervals and so on. Okay, so and K is the intersection of these K's. That's the definition of Cantor set. So what is the upper length? Let's just, this lambda super hash of K, what is it? See, a natural covering is Kn itself. Kn's are elementary sets. Note that Kn is an elementary set. It's a union of intervals. So this is less than equal to lambda hash. It's equal to length of Kn for any. Since K is contained in Kn, this length should not be more than that. But what is the length of Kn? So here it is 1. Here it is. There are two intervals of length 1/3 each. And here it is 4 intervals of length 1/9 each. So what will be the length of Kn? It will be
2/3 power n.
Yeah, exactly. There are 2 to the n intervals, each of length 1/3 to the n. So Kn is a union of intervals of length 3 to the 1/3 to the n, and there are 2 to the n of them. So this will be the thing. And this is true for all n. So that means I have to take infimum. So when I let n go to infinity, I already get 0. So lambda hash of K, there may be many other ways of covering, but I am looking only at the infimum. So if I get a candidate, if this infimum was 1.5 or something, okay, whatever it was, if its infimum was non-zero, I wouldn't be able to conclude much, because then there are many other possible ways of covering. I would have to worry about that. But when the infimum is 0, then it is clear that okay, lambda super hash of K is 0. So hence, and this is anyway equal to lambda lower hash of K. Okay, because this is greater than equal. So lambda lower hash of K is anyway greater than equal to 0. So when you compare that, you see that lambda K is Jordan measurable and length of K is actually 0. So here is actually a point. So this is actually Jordan measurable and this is 0. So here I could ask you a question. What happens if you delete in some other way? So suppose to think about, what if middle alpha interval is deleted each time? So middle alpha proportion. So you fix alpha in 0 to 1. So fix some alpha. Here it is 1/3. Each time I deleted 1/3. Suppose I do some other alpha. And what I do is, in the first stage, I delete middle. Middle is clear, right? So centered interval, the same center, you delete the alpha proportion of it. And in each of the remaining intervals, you keep doing the same thing. So that is one question. And another question is, what happens if I do fix? I don't have to delete the same number each time. Suppose I fix a sequence of numbers, alpha n's, going to alpha n's in 0, 1, and delete middle alpha n. So n is greater than equal to 0. Middle alpha n proportion at stage n. I will not try to write it more formally unless the meaning is unclear. If so, please let me know. And I am suggesting that following generalizations of Cantor set. So this second one is more general. So let me explain that. So you have some sequence of numbers, alpha naught, alpha 1, alpha 2, alpha 3, and so on. Okay. And what I do is, they are all numbers in 0 to 1. So in the first step, I delete the middle alpha naught proportion of the thing. So if alpha naught was half, that means I take centered around the center of the first interval, I delete an interval of length half. So it will go from 1/4 to 3/4 in that case. And then in the remaining intervals, I delete the middle alpha 1 proportion of the interval and so on like this. So in all cases, the final set K is defined as the intersection of these. So I will leave it for you to think about what will be are those things Jordan measurable, and can you tell what the lengths are for such things? Okay. So I will leave that. But what I want to now give is an example of something that is not Jordan measurable. Okay. So Cantor set was a candidate suggested. It was a good candidate, but didn't work. So any other candidate for something that is not Jordan measurable?
No.
Yes. Sorry, I could not hear.
Set of natural numbers.
Set of natural numbers. So set of natural numbers. Well, what? Okay. So what is the Jordan measure of the set of natural numbers? So you are suggesting Z.
Yeah.
So I say that it also has length 0. Okay, sorry. Okay, you are right. You are right. So that is not possible. Yeah, you are right. Okay, so the way I have defined, no, you are right. But let's have it is a bit too big because I cannot enclose it in. If I enclose it in finitely many intervals, one of the intervals has to have infinite length. This is the reason. So you are right in the way I have defined. It is going to have infinite length. But how about a bounded set which has?
Okay.
Set of fractions in 0, 1.
Huh?
Set of fractions in 0, 1.
Okay. So let's take rational numbers in 0, 1. Okay. So let's take this set. Let's call it A. Okay. So this is a dense set in 0, 1. Okay. So what can we say about this? So what is lambda lower hash of A? So to get lambda lower hash, we have to find a bunch of intervals which are contained inside that, whose union is contained inside rationals. So what can you do? What are the intervals that are possible? Right. So empty set or singletons are possible. Singletons are allowed as intervals. So I can take a bunch of singleton rationals, but any interval, non-trivial interval, contains irrationals. Therefore, this is actually, there are no non-trivial intervals. So if you do this, all these ij's have to be singletons. Therefore, their lengths are 0, and this is going to be 0. Is clear. Okay. What about lambda super hash of A? So I want a bunch of intervals whose union contains all the rationals in 0 to 1. That will.
I think it's 1.
It has to be 1. So think about it. Both of these are correct. So this I explained. So think about this. If you have finitely many intervals, which I mean, it is very easy to figure out why. If you have finitely many intervals, you can even write down explicitly as A1, B1, A2, B2, AN, BN. We are not saying they are closed or open. They can be either. But then you have to see that you can order them A1 less than A2 less than AN. Then you kind of see that these intervals will have to cover the entire 0, 1 actually. So therefore, the sum of their lengths is actually going to be at least 1. So this lambda hash of A is 1. Okay, so I will leave you to check. So write down a proper proof. Why I'm going to write an honest proof that this is 1. Okay, so write an honest proof that this is 1, and then you see that hence not Jordan measurable. Okay, so this is not Jordan measurable because this is, although it is a bounded set. So the Z, okay, Z was also a good example, but unbound. So there are two reasons why length may not be there. One is it's too big. One is, but that is okay. So that's why I excluded Z. This is better. It's a bounded set. Still, according to Jordan prescription, this is not assigned a length. So we haven't said what to do if these two are different. What will you take as length? Okay, so there are many sets you can come up with which are not any dense set in 0, 1, countable dense set in 0, 1, you will see has the same problem. So this. If you take any countable dense subset of 0. Okay? So the same problem. So there are many sets which are not Jordan measurable. So Jordan measure is a natural, Jordan measurable sets are a natural way. It looks natural, but it is still limited because many sets we are not assigning their lengths, assigning them lengths. Okay. So, okay. So what do we do beyond that? But before that, let me take questions. So are there any questions so far? So this is Jordan measurability is one attempt at trying to extend the notion of length. It does extend it, but not satisfactory enough. I'm not saying why it's not satisfactory enough. Just saying that there are many sets, natural ones you can write down, which are not Jordan measurable. That's all. So we will come up with something. Maybe when it was defined first, it was not felt to be a big shortcoming, but we now know that there is actually a much better thing which will in which it will be difficult to come. I mean, we will see that there is a much better notion of length, and we will define that. Okay, so we'll go there. But before that, if there are any questions, please ask.
Sir, is the length of all Jordan measurable is 0, or like is there any set Jordan measurable set which length like lambda a is not 0?
Oh yeah, sure. I mean, so if you take an interval, this is a good question, because okay, so if I take the interval itself, so here is another example. Suppose I take A to be, let's say first definiteness closed interval. Is it Jordan measurable? Okay, so let me say it is Jordan measurable, and its length is whatever you want it to be. It would be a bit strange if, see, there is an infinity. This is not obvious. Okay, so don't treat it as obvious because I started with lengths of intervals, but now for any arbitrary set, I am doing some strange thing like taking the infimum over this and supremum over this. Now, what is clear is that, so this is what is clear is that lambda lower hash of A is greater than or equal to B minus A. Is clear. Okay, why? For example, I could take the interval AB itself is contained inside A, therefore you see that it is at least B minus A. Or even if A was an open interval, I could take a slightly smaller interval contained in it. Therefore, in this supremum, one candidate is a single interval contained inside my interval, almost covering the whole thing. So I get that the lower length is at least B minus A. Is it clear that the upper length is at most B minus A? Is it clear that the upper length is at most B minus A?
Well, again, we can use the same interval, right?
You can use that, but that's only one way of covering. How do you know there is not some better, clever way of covering it with intervals whose sum of lengths is less? Right? In some sense, this exercise is actually subcase of an exercise I gave here, that lambda hash of rationals intersection 0, 1 I said is 1. Of course, if so here, I mean, if you could cover 0, 1 with intervals whose total length is less than 1, you could also cover the rationals inside. So here, this is something that maybe I should have asked before. So can you possibly cover AB in a clever way such that the length, sum of lengths is actually less than B minus A? Is that possible?
Yes, we can take A minus epsilon and B plus epsilon.
No, that is, but that will still have more, right? That will have, if you take A
Definitely
minus
not with
epsilon,
finitely many, right?
so if you, no,
Yeah, I am taking
yeah,
one, just one interval.
you are taking a single interval covering. This has length B plus A plus 2 epsilon. So but epsilon is arbitrary. So this will only tell me that lambda hash of AB is less than or equal to B minus C. That is clear. That is also, I mean, sorry, what did I say? Oh, sorry. This is, Okay, what did I do? Oh, okay, sorry, that it is less than equal. Okay, sorry, I confused myself. Sorry. You are right. Lambda, okay, sorry, there is no, did I make some mess here? No, there is no problem. Okay, so this is not difficult. Okay, sorry. I made a heavy weather about something. So you can enclose A inside sets which are of the same thing, and on the above also you can do the same. Okay, so there is no problem about this. So intervals have Jordan. Okay, I was confusing with something else which will come later, but you are right. So there is no problem. So it is correct that lambda hash of uh, so since you can enclose it inside the interval AB, this infimum is at most B minus A. But since you can put an interval of almost the same length or even the same length, its length is lower length is at least B minus A. From these two, it implies that they are equal, and so interval is Jordan measurable, and its length is exactly B minus A. So yeah, so there are all these sets. In fact, all elementary sets are also going to be Jordan measurable, and so on. And if you answer this question, so this was for your question, can it always be zero? But not necessarily. These are examples, and even if you do this exercise of a generalized Cantor set, you will find other interesting examples where the length can be something non-trivial. Okay, sorry, I confused myself about something else. Okay,
Okay, thank you, sir.
any other questions?
Sir, so how do we extend these definitions to infinite sets?
Well, I have infinite sets here. Q intersection one is an infinite set. You are talking about unbounded sets.
Yeah, unbounded sets. Sorry.
Yeah, we'll worry about that. I mean, so but anyway, this notion is not so great. I mean, it's limited compared to something else we are going to do. See, there are in so one should remember two things. So the thing is, in measuring lengths, just as in finding integrals of functions, there are two reasons why some function may not be integrable. One is that it's too big. You are trying to measure too large an area. So in principle, you should say infinity is the answer. So that is one reason why something is not integrable or some area is not defined. But that's not the interesting one. The interesting point is that what you see even in Riemann integral is that even if the function is bounded, for strangely, the upper and lower sums need not match. And then there is a local abstraction to measuring the area under the graph. That is the more tricky point, actually. Not that it is too big, but because it is somehow the local structure of your function is preventing you from measuring its length. So that is what I would like to emphasize here. So let's not worry about unbounded sets. Even with bounded sets, there are many sets for which we cannot measure the length, like here, according to this notion. So we will go for a more general notion. But this is a good thing to keep in mind. This idea is there. And what is what? Okay, but is that all? I mean, is that uh, okay? So does that answer your question? Sort of. Don't worry about unbounded sets. That's not the.
Yes.
Okay. So
So,
go on.
sir, the problem is, I mean, you are fixing some fundamental things like interval, and then you define the length to be b minus a,
Yes.
and then stepping ahead the definition of the measure, right?
Yes.
So the problem is the interval. I mean, uh, if if you take so much nearer points like rationals, they're so dense. So that's why the lower thing is not the measurable thing.
Okay. So you are right. Maybe you are foreseeing some difficulties with how to get out of this. Maybe we'll come to that.
Yes.
You are right. Intervals we will use, but there is something else. So, but you are getting to the nub of the problem. But before that, I want to suggest a candidate. Hold on. I mean, so we are saying this is not good. Are we being too hasty in dismissing this? Okay. So what is our problem? Our problem are sets where lambda lower hash doesn't match with lambda upper hash, right? But who cares? Why not just define just let's for definiteness just take the upper length to be the length of A for any subset. Okay, so far I was trying to say that maybe this is not good because some things are not Jordan measurable. But why care? Let's not worry about the lower length at all. Let's just worry about the upper length. Okay. I mean, if you like the lower one, you can take the lower, but I have for definiteness taken the upper one. Why not just define that to be the length of A for any set A? Okay. Well, does that violate? I mean, the only thing I wanted was monotonicity. Will monotonicity be preserved if A is contained in B? Okay, first of all, this will agree. So what is good about it is it agrees with the common definition for all Jordan measurable sets. Because all Jordan measurable sets are fine. So their lambda hash of A, lambda lower hash of A are all the same. So that is fine. But it has the advantage, it is well defined. At least all bounded sets. If I have a bounded set, I can always cover it by one interval, right? So it will have any bounded set will be assigned, will have finite length. So that is also there. And most importantly, it satisfies monotonicity. I mean, that's the only requirement I said. It still satisfies monotonicity. That is why, I mean, I'll just say it in words. If A is contained in B, is lambda super hash of A less than equal to lambda super hash of B. Indeed, you take any A is contained in B, you take any covering of B by an elementary set that will also enclose A, right? So the whatever infimum I am taking for a larger set, it's a smaller collection of numbers. There could be, so if A is contained in B, there could be elementary sets covering A but not covering B, but every elementary set that covers B covers A. Therefore, the infimum over a larger set is smaller. Therefore, monotonicity is also okay. So why not? What's so bad about this? So, okay, so we can this way define length. Okay, so well, fact is monotonicity is not everything we are asking for. I mean, we have some other notions of length, what length should be, which have not been made explicit. So let's try to say one of them. Then maybe it will be clear. So another let's just say desirable property of length. So it is the following, that if A and B are disjoint, then the length, or just let me write length of the union, so this is now a disjoint union, should be the sum of the lengths. Okay, so this is another desirable property of lengths, that if I have two disjoint sets, the length should be the sum of lengths. We kind of, that was what we had in mind when you defined the elementary set to have length, which is the sum of the lengths of the constituent intervals, right? So why not, I mean, ask that in more generality. This seems a reasonable and desirable property of length, and this is very badly violated by lambda super hash. Okay, so this is why, how is this violated? Can you give an example?
Rationals and irrationals between 0 and 1.
Yeah. So this is, so let me write, this is violated. So this is called, okay, let's call it finite additivity. Okay, why the word finite? We could call it additivity. Just I'll come to that. So additivity, this is violated by lambda super hash. Okay, now can you tell me what is the example?
Yeah, rationals and irrationals between 0 and 1.
Okay, you take A to be rationals intersected with 0, 1, B to be irrationals intersected with 0, 1. So this is the complement of rationals. And so now A intersection B is of course empty. And A union B is the entire 0, 1. Every number is rational or irrational. But we know that lambda hash of A is 1. This also is a dense set. And lambda hash of B is also 1. Okay, I mean, I said earlier countable, but you can easily see that lambda hash of B is also 1. And lambda hash of A union B is also 1. Intervals have length 1, that we argued. I mean, the Jordan measure will give that 1. So here we have a violation of this additivity principle, which we would like to have. So this is actually a shortcoming, serious shortcoming of the Jordan measure, Jordan measurability. Okay. So we don't. So this is the reason why we can't just say let's take lambda hash and be done with it. We'll want something more than this. Okay. So that is what I will now go for. So that is the next notion. Okay. So okay, so now we can go to a more. So that was the shortcoming. So that this is not finitely additive is our problem. So that is why we are going to go for a different notion. But it is nevertheless good to spend time on Jordan measurability, although it's not something we'll ever use. It's limiting, but it seems a natural one to try first. So it's not, it's time well spent, although we will not use it. We'll go for something that is more general. Now you also it contrasts what so once you see something that doesn't work, sometimes helps you in understanding why the things that work actually do work. So let's now come to that. So here I define a new notion like lambda hash, another candidate at length, okay, of length. So this is okay. So definition. For any subset of real line, define it is called Labag outer measure. That's the technical name. Lambda superstar of A. Okay, it's like a lambda super hash, but there will be a difference. So like lambda super hash, it will be an infimum of what? So what we do is we cover A in intervals. So I1, I2, etc. are intervals that cover A. Okay, so this is actually okay. And then if they cover, and then I take the sum of lengths of those intervals. So the thing is, this is a countable cover. Okay, so that is the one important point is there are countably many intervals, I1, I2, dot, 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 not finitely many. Okay, so that is one of the things. And then I am not even asking for disjoint. Disjoint is, yeah, so I'm not asking for disjoint, but that will only make it worse. So it is okay. So so I take any countable cover of A by intervals, okay? And then I take the sum of lengths of the intervals. That should be, A should not, since A can be contained inside that, if they overlap, the sum of lengths will only be larger. Therefore, this number should beat whatever notion of length I have, and I take infimum over all possible coverings, and I call that the outer length or outer measure of A. Okay, so this is the definition. So key features to note, we are using countable covers. So this countability is a running theme in the entire course. This is actually countability is absolutely one of the running themes in the entire subject actually. So this makes all the difference in the world. So one of you was saying, maybe Karambe, somebody was saying that Maybe the problem is that I considered intervals. No, the problem is that I considered finitely many of them. So if you consider countably many of them, it changes the entire game, as we are going to see. Okay. So, but here there are alternate possibilities here. So I didn't ask for disjointness. So sometimes one can restrict, if you want, you can only take open intervals or closed intervals or such things. So you can also restrict to, that is not, those are not so important. But since I'm going to do it later, so let me write what kind of intervals are nice. You might feel open is nice, but for some reasons in measure theory, it is always nicer to take left open, right closed intervals. So let me write LORC intervals. So this means left open, right closed. So things like A, B. Okay, so left open, right closed. Okay, I mean, it doesn't make a difference. Okay, why it doesn't make a difference, we'll leave later. It's not so important. For now, if you want to take all intervals, because any interval, if it is closed interval, you can just slightly enlarge on the left and make it open. And if it is an open interval, you can slightly enlarge on the right and make it closed, and so on. And without increasing the total length, sum of lengths much. Okay, so that is the point. But anyway, let's just define it like this. So for now, this is not important, but later this will be technically convenient. These left open, right closed intervals are technically convenient. So I just threw them out there. But don't worry about this issue now. The main point is countable covers. That makes all the difference. Okay. So now what happens to the problems that sets that we had before? Okay, I have not yet defined what is Lebesgue measurable. So this is lambda star of A. Okay, so what happens to, let's look at some examples that we had before. So what if I take the interval, which is, for example, what if I take the interval itself, about which I was making a bit of a fuss. Let's take a closed interval, A equals AB. So what is lambda star of A? So this is going to be a candidate for length for us. So better not change it. So I claim that lambda star is B minus A. Okay. So we have to show that why that is the case. So I want to say that if you do this, it's still true that the intervals will have the length as before. Now here it needs a proof for the reason that you know that it is okay. So why would you say that it is actually, so it needs a proof. Why does it need a proof? What is clear is this is clear because take I1 is AB and I2, I3, etc. You take them to be empty. Or if you are worried that, oh, did I allow empty intervals here, you take singletons. Or if you don't like singletons, you take small intervals so that their sum is also small. For example, you can take I2 to have length epsilon, I3 to have length epsilon by 2, I4 to have a length epsilon by 4, and so on. So we'll come to this type of idea. When you work with countable, this trick is if you have never seen it before, first time you see, it's a kind of funny trick, but it is a common one we will use. So anyway, I am allowing in empty intervals also. So you can take I1 to be AB and all these to be this. Then this sum will be B minus A. So the infimum will be at most B minus A. That is clear. But can we not do better?
Monotonicity?
Monotonicity of what?
The cover. Right?
No. Monotonicity of what? It is clear that lambda superstar is monotone. That's correct. If A is contained in B, lambda star of A will be less than equal to lambda star of B. So, but okay, so let me make a point here, because sometimes in mathematics we keep giving proof without saying why we are trying to give a proof. Sometimes it is important to realize that something is, I mean, because it looks obvious, why should I give a proof? So maybe this will help you to realize that you do need to give a proof. Suppose I define some other notion, lambda star star of A. Okay, infimum of, suppose I take the squares of lengths. Cover A. Okay, by the way, cover A means that the union is contains A. Okay, that is what it means. I didn't write that. So suppose I define it as infimum of sum of squares of the interval lengths. Then what will be lambda star of an interval like 0, 1? So what I can do is I can cover it with 0 to 1 by n, 1 by n to 2 by n, and so on. I can use ij is j over n to j plus 1 over n, 0 less than equal to j less than equal to n minus 1. So what will that give me? The length of this interval ij is actually 1 by n. I'm going to square that and add n times, so I get 1 by n. So you see lambda star of 0, 1 in this case will be 0.
So you should write lambda star star.
Ah, yeah, thanks. So this will be lambda double star of 0, 1. If I define lambda double star with infimum over sum of squares, suppose I were to think that the length of an interval should be b minus a square, of the interval ab should be b minus a square, then this would lead me to this new notion of lambda double star, in which lambda double star of 0, 1 would not be what you started with assigning its length as 1, because that's the square of 1. But after you take the infimum, it is actually changed to 0. So maybe this is a, I mean, okay. So this is a, why would you do square here? Why, okay. So, but it illustrates that you do need to give a proof here that you haven't changed it. It could become smaller. It could certainly become smaller. It cannot become larger because you can certainly use the interval itself. So if you use I1 equal to 0, 1 itself, then the sum of squares will be 1 and the others I don't use, so I get 1. So it is less than equal to 1. You can't go higher, but it can go lower. That's certainly possible. So which is why we do need to give a proof here that lambda star of A hasn't gone smaller than this. How do we do that?
Sir?
Yes.
We might try to to define lambda lower star of A and show that lambda lower star of A is less than lambda upper star of A and show that both are equal to 1.
Well, yeah, certainly a possible way, but it's kind of going to be redundant. So we will not define any lambda lower star. Actually, lambda lower star, you see, many times intervals are not contained in our set at all. So that can be a problem. If we are going to use intervals, many of our sets will not, lot of sets can be covered in intervals, but you can just think of Cantor sets or rational numbers or irrational numbers. These things do not contain any interval. So asking a set to contain intervals is more restrictive than we would like to do. Okay, so I will not define a lambda lower star in that sense.
I mean, if lambda star of A is b minus a plus epsilon, then we can find an interval which is length of b minus a plus epsilon by 2, which is strictly less than of that.
No. How would you do that? I mean, so you have to find intervals which cover the interval AB, and you have to say, then you have to set the sum of at least. Let me actually prove it. It is not entirely trivial, so let me actually prove it. Okay, so because you use something, a little bit something is actually used. So let's see. Suppose, to show the other way.
Sir, one query.
Yes.
Sir, how lambda star 0 comma a equal to 0? Like it should be 1 by n, right?
No, 1 by n, but n is arbitrary, right? I take infimum.
Oh. Okay.
I take infimum over all possible things. So this is just one candidate, and I have to take. So my set of the set on which I am taking infimum contains all the numbers 1 by n. So its infimum has to be 0.
Okay. So like we can think n equals to infinity. So then infimum.
Yeah, I mean, so it is a set. Infimum means it has to be smaller than all those numbers. So what you get from here is that lambda superstar of 0, 1 is less than equal to 1 by n. And that's true.
Yeah. Okay.
Therefore, it is actually 0.
Yeah, okay.
So,
Yes.
so is showing that kind of disjoint additivity property for this lambda star enough to prove this thing?
Well, okay, we'll come to those things later. It is easier than, so to speak, I mean, let me do it actually. So this is a bit easier than that. So the thing is, so suppose, let's go by definition. We have nothing else to go except the definition. Okay, so it is the infimum. So, so what we can do is, what is by definition of infimum? Find a cover by intervals such that, I mean, of course, this is covering AB, and sum of the lengths is less than lambda star of this set plus epsilon. So fix epsilon. So by definition of infimum, I can always find a set element in my set which is smaller than the infimum plus an epsilon. So that's all I'm doing. I'm finding one cover such that it attains it almost. There is nothing that may attain the minimum, but it will attain it up to epsilon. That's the definition of infimum itself. Okay, so this we do. Now what we do is, I did not say what kind of covers intervals I was doing. So if necessary, enlarge ij by, I only enlarge a little bit by epsilon over 2 to the j to get an open interval ij tilde. I have written it just in words. I hope it is clear. In other words, if ij was, let us say ij was 0.1 and 0.2, something like this, then what I do is I just enlarge a little bit to the left and to the right, but so that I don't enlarge by more than this. Okay, at most, by less at most. So maybe I will take 0.1 minus epsilon over 2 to the j plus 1, and I take here 0.2 plus epsilon over 2 to the j plus 1. No loss, right? I mean, so I just enlarge it a little bit, and this new interval is my ij tilde. So I just make everything open intervals so that they are, I mean, so, and their lengths are not too small. So then if I take the sum of lengths of ij tildes, the reason I don't want to enlarge too much is I want this sum of lengths is also small. Well, this will be less than equal to sum of ij plus epsilon over 2 to the j equals 1 through infinity. And what is epsilon over 2 to the j? If I add up, I'll get epsilon. So I get less than equal to lambda star of a plus 2 epsilon. So in other words, all I am saying is that by taking only open cover here, I can make this, all I'm saying is that this infimum would not change if I restricted myself to open intervals, which is something I mentioned here. I did not explain earlier, but this is the trick. You can restrict yourself to open intervals and make this, and the infimum doesn't change for this reason. Okay, so now we have ij tildes which are open, but what can you say about this? A bunch of open sets whose union covers the closed interval AB, then there is a finite cover. Because AB is a compact set, finite subcover, say, which we will take as A1, B1. Okay, they can be some I5 tilde, I23 tilde, whatever they are. let's say we have some finite cover which is like this. Okay, finite subcover, which I will write like this. With without loss of generality, I arrange it so that A1 less than A2 less than AN. If you want less than equal to. Is okay. By compactness of the interval, this closed interval AB, I can take a finite subcover which does this. And I just take that finite subcover and arrange it in order so that this interval starts before this interval starts before this interval and so on. So now, what can I say? So I have to cover this 0, 1. So what is certainly true is that 0 has to be covered and A1 is the smallest. So A1 is less than 0. Certainly, because A1, B1 is the lowest one. And similarly, B1 is bigger than 1.
Bn, right?
Oh, sorry, Bn. Bn is bigger than 1. Thank you. So the lowest one should cover this. So I have a bunch of intervals which are covering. The picture makes it very clear. So I have some intervals which cover like this, right? So they have to cover it. So the point is, so the first lowest, the first interval should cover this. Second, last interval should cover this. And also these intervals should overlap. The second interval should start before the first. I mean, before the first ends. Well, yes, that's right. One of the intervals will have to start before this ends. That's the point. Okay, so A2 has to start before, because if A2 was here, then all the A3 and all would be here also. So what I'm saying is, if A2 was bigger than B1, so this is A1, B1. If A2 was bigger than B1, if it was like this, then A3 and all would also be larger. So this part would be uncovered, would remain uncovered. Therefore, I should have A2 is less than B1. So, agree? And similarly, I should have B2 less than A3. Is that also clear? So here I will have A2 to B2. The next interval should start before that. Otherwise, again, the same problem. If it starts later, all other intervals will start even later. So there will be a problem. So A3 should be below B2. Oh, sorry. What did I write the other way? I wrote the other way. Sorry. B1 should beat A2. Okay. A2 should, yeah, sorry. Let me write it properly. So these are the conditions. So let me write all the conditions. So A2 should start below B1. A3 should start below B2 and so on up to, and AN should start below BN minus 1. Any questions? Is this clear? Okay, I don't know how some things get deleted. I just do something. Yeah, so here there was a line, wasn't there? Okay. Okay. Yeah, so is this clear? So these intervals have to satisfy this. Okay, so then what is the sum of the length? So let us call this I1 hat, I2 hat, In hat. Obviously, these are part of this. So summation ij tilde in my subcover is greater than equal to summation ij hat. J equals 1 to n, and remember this is at most lambda star of A plus 2 epsilon. Okay, lambda star of A plus 2 epsilon beats the sum of all the intervals ij tilde. I have chosen a finite subset of them which are here, and this is nothing but B1 minus A1 plus B2 minus A2 plus up to Bn minus An. But now you see this B2, what I can say is, yeah, so what I wanted to say, so this I will write as minus A1 plus B1 minus A2 plus B2, that's how I should have written, minus A3 plus B3 and so on, in the end minus An plus Bn. This is how I should have written. Okay, so this is exactly the length. Now the thing is B1 minus A2 is non-negative. B2 minus A3 is non-negative. and so on up to bn minus 1 minus an is non-negative. So I get is bn is greater than equal to bn minus a1, and bn is more than 1 b. Okay, here I should have, this was a and b. Yeah, bn is more than b and an is less than a. So this is more than b minus a. And that proves that lambda star of a plus 2 epsilon beats that, and epsilon is arbitrary, so you get that this is greater than equal to b minus a. Okay, so we use the compactness here to reduce to a finite cover and do the argument. Okay, so it was not entirely obvious that interval should have length b minus a, but that is true. Okay, any questions about this?
Oh, why does the finite cover have a smaller length than the other one?
This is a subcollection. This is only the I1 hat is one of these ij tildes. I2 hat is one of the.
Okay, right. Thank you.
This is a larger sum. Yeah, it's not subsets of those. It is actually a subcollection. Okay, is that clear? Okay. Yeah. So it will be something that will be useful for us. We will use this later, but it is very important calculation that we did. I mean, the small thing that we did now. Okay. Any other questions? Okay, so let's just go over some other sets. What happened to our rationals? Q intersection 0, 1. What happens to that? What is its lambda star? So we claim that lambda star is actually, I mean, I don't even have to take Q intersection 0, 1. I just take even the unbounded set. Okay, so somebody was saying Z, but I will even do for Q. I claim that lambda star of rationals is 0. Okay, all because we allowed countability. Okay, so this is the thing. So why is this? So, well, it's the argument which I kind of mentioned up there, but let's write it out. It's something that you should internalize. Enumerate Q as, let's say, R1, R2, etc. So we can write it in a list because it's a countable set. Now, use the intervals ij to be rj, fix an epsilon, and use the intervals epsilon minus 2 to the j, rj plus epsilon over 2 to the j. So then this union ij covers rationals because the jth intervals contains the jth rational. Okay, the whole flexibility comes from earlier one because we have countably many. We can make these intervals smaller and smaller and smaller. So we are doing that epsilon over 2 to the j, and so this is true. And what is the sum of lengths? The sum of lengths, each the jth one has length 2 epsilon over 2 to the j. And we are summing j equals 1 through infinity. 1 over 2 to the j sum is 1, so you get 2 epsilon. So therefore, lambda superstar of Q is less than equal to 2 epsilon for all epsilon positive, implies lambda star of Q is 0. Okay, so rationals have 0 length. This is true. Okay, this will remain. This will remain with us. Rationals will have length and it will be 0. So the length of rationals is 0. You cannot play this trick with irrationals. With irrationals, you cannot enumerate them like this, and you cannot do this trick. Okay, what is the length of irrationals? We'll come back to that. But okay, so this is how it is. Okay, I have 4 minutes, so let me just end with the point. So what is it? So now we had this earlier. We had this Jordan measurability. We had this lambda super hash, lambda lower hash. If they agreed, that would define the length. And then we saw that it was not satisfactory for the following reason, that it was violating the finite additivity, that there are sets for which are disjoint, but their length is both the lengths are 1 and the length of the union is also 1. Now we have a new notion of candidate notion for length, namely this outer measure, which is the infimum of the sum of lengths of intervals over all countable covers. Now, does that solve our problem? Monotonicity of this is clear, right? For the same reason, if A contained in B, well, any cover for B will also cover A. So monotonicity is clear. What happens to this finite additivity? If that is solved, then of course, excellent. So here is the issue. So there exists A and B. There exists A and B such that A and B are disjoint. A union B is 0, 1. Lambda star of A is 1, and so is lambda star of B. Okay, of course, this is also lambda star of 0, 1 I already know is 1. So it looks like back to the same problem, right? So the same problem, Jordan measure, what was the problem? We had two sets, A and B, and A whose intersection is empty and whose union is 0, 1, and their lengths are all 1. So exact same problem here. So what is the progress we made? So this new notion of length for all the praise I gave is actually not is having exactly the same problem, so violates finite additivity.
So what are the sets?
Well, that is where the entire point is, but this is better. Why is this better? Because I haven't told you what the sets are. It is extremely complicated to tell what the sets are. I will tell you next time. Okay, so that is where the saving grace is, that in Jordan case, it was very easy to come up with these examples. In the Labag case, it is actually very complicated to come up with these examples. It's quite hard. You can try. If you have not seen it, I mean, there is no way you will get it. I am more or less sure. It's almost impossible to think of it. It is, I mean, okay, maybe you can, but it is very difficult to think of it. So that is where the point is. So it's still what is going to be our resolution. It's not that it works always, but it works in far more situations. So what will be the resolution in measure theory? The thing is, we will limit our notion of sets.
It's 5 o'clock.
We will limit our notion of sets to a subclass of, we will limit our notion of length to a subclass of subcollection of subsets. We will not define length for all subsets, but we will cover a wide collection of subsets, and we'll be happy with that. That's what will happen. Okay. So that is the point. So it is 5 o'clock. So maybe, yeah, maybe I will leave it here and continue, take it up next time. Okay. So one of the things is to see what these sets are which violate it. And then there is another question, why lambda superstar? Maybe there is some completely different way. So maybe you should ask the question, is there any way to define length so that for intervals you get the length b minus a, and which is finitely additive? Maybe that is what one should ask. Maybe one should not start with candidates, but one should ask, is there some way of defining a notion of length such that for intervals it will give you b minus a, and and it will have finite additivity? Is that possible? Well, its interesting answer is yes, but we will not accept that. Okay, we will talk about that next time. Okay, so I will end the class here. Oh, somebody raised hand. Sorry, I don't get to see the Teams thing when I am on the OneNote. So you may ask the question now. So I stop recording now, or maybe I keep it till the questions are over. Yeah, if there are questions, please ask.
Sir.
Yes.
So last class we had discussed measures of subsets of the counter set, one half of the counter set in particular. I was kind of confused because if we have finite lengths, it's easy to compare them. But if the Cantor set itself has zero length, how do you compare zero and a length that is that comes from a subset of this set?
That is completely true. Yeah. So we don't know. So we haven't answered that question. But you will agree is that whatever length you assign to the left half, you should probably assign the same length to the right half. Or do you have any reason to?
No, that by symmetry is acceptable. Does this have anything to do with the idea of so-called relative lengths?
No, that's true. But there I was talking about relative length. So if I were to say that the whole Cantor set should have length 1, then what should be the length of the left half? I didn't say the length of the left half is 1 half.
True,
I said relative to the full Cantor set, it is 1 half.
I see. All right. Thank you, sir.
It is a very good question. It is the same problem. I mean, it is. We will address this question and we will give the answer. What is the actual way of measuring lengths there? This there. But it is the same problem that arises in probability when you try to condition on 0 probability events. It's a similar issue. If you have seen probability, if not, forget that analogy. It is an issue. We will come to that later. Any other questions?
Yeah, quick question. Relating to where violations occur, is there any way to possibly divide the irrationals? Like, I don't know the answer, but is there any way to divide the irrationals like into 2 sets, such that both are in both these sets have 0 distance between them?
Well, that is very easy. I mean, so distance 0 is very easy. For example, I mean, you can do lots of things, right? I mean, why? I mean, so yeah, I mean, there are many ways to do it. You are getting at the right sort of thing, but it's not just making them 0 distance is not going to be sufficient. You have to, I mean, you are trying to say how to get a violation of this. Is that what you are trying to get at?
Yes.
Yeah, so violation of finite additivity. Yes, these 2 sets have to be very, very enmeshed with each other in some strange way. And but merely making them 0 distance is not going to be enough. What all you are saying is you want to split irrationals into 2 dense subsets, disjoint dense subsets. That is easy. That can be done in many ways. That's not going to be sufficient. We will do it next time. I will show next time how to get this violation.
So what will be the measure of irrationals in 0, 1?
It will be measured, it will have a length and it will be 1.
Okay.
Okay, so by the way, I have put the notebook on the, I mean, I linked the notebook on the website, so hopefully people can see it. We will be able to view it. And also I put the recording, I put it in under files. So I hope to do it, but if I don't do it, please remind me because I tend to forget these things. Yeah. So either today evening or sometime I will put the recording in the under the files. If I forget, because after some 18 days it gets deleted automatically. Yeah. Okay. So any other questions? Not, let me stop the recording then.
So for completeness, I was thinking something like sine square of n factorial whole to the root 1 by root n should work.
No, I mean, so you are talking about which one? The Chinmay's question in the beginning?
Yeah. Yes.
So you are talking about Riemann integrable function. So you are taking sine nx, is it? Or which one? Sine?
I took sine square n factorial x and then raised it to the power 1 by n.
Okay, so okay, maybe. I mean, I have absolutely no idea. Why did you do all that? No, it may work, but why n factorial? Why to the power 1 by n?
N factorial because that way you get to cover all the rationals as n grows. I mean, all the rationals times pi, all numbers of that form will give you.
No, but you are talking about in the space of Riemann integrable functions, right?
Yeah.
So all these functions are nice. So the thing is whether it will form a Cauchy sequence which converges to something else. That's the question you have to ask. In this case, so if this works, I think just taking sine nx, sine squared nx itself should perhaps work, I suspect.
No, for this one, if you take if you converge, so if you take the limit of the functions, you'll get something that's zero on all numbers of the form rational times pi.
No, but you are taking a limit along pointwise limit, right?
I'm taking the limit over n, right? The functional limit.
Yeah, you are taking the limit in the pointwise limit of the functions. But the problem there is to construct a set of sequence of functions that is Cauchy in the metric of Riemann integral and not converging to anything there. But okay, maybe this is a starting point for that. Maybe you can produce this candidate like this, but it is not the question of what happens at points, though that can be useful.
Right, I see what you mean. Yeah, thank you.
Okay, so yeah, actually I'm not. Yeah, I so think about it. Then we'll discuss. If you don't get it next time, when we'll discuss. Yeah. So next class is next Tuesday, right? Okay. So let me now stop the recording. I can hang around for a few minutes if